Okay, video lecture 2.4. In our first three video lectures, we've dealt mostly with numbers, and we've discussed some of the ways that we have to look at numbers, tweak the numbers, change them, and round them, and of course our new friend sig figs, or otherwise known as significant figures. This next section of notes, we're going to talk about measurements, but not going to actually look at the numbers. And so it's a little bit of break from what we've been doing this chapter. We want to discuss measurable quantities of matter. If I have a sample of matter, and again, it could be in any phase, a solid, liquid, gas, how could I measure that matter? What could be some quantities I could measure, some properties I might be able to measure of that? And so the first one that we want to come to is how much space that amount of matter takes up. And that really depends on whether we're dealing with a liquid or a solid or perhaps even a gas. But the space we talk about is called volume. Volume is the amount of space occupied by something, by an object, or it could be a substance. Depends on how we're measuring. If it's a solid, we're going to measure it by our old volume equation that I'm sure you've seen before. Length times width times height. And if you remember, the fundamental unit for length was a meter. If those were all meters, meters times meters times meters gives us meters cubed. And there we see the units in the definition as centimeters cubed or meters cubed. But however, if we're not measuring something in solid or something that fits in a container like a solid would or possibly a gas, we might be looking at liquids. And hopefully you recall that we measure liquids using a graduated cylinder. And this would be measured in milliliters. If you have 1,000 milliliters, you would have 1 liter. So if it was in much larger containers, you might go with liters, but more commonly it's a milliliter. And in parentheses there you have a unique conversion rate. A milliliter is about the same as a cubic centimeter if the packing of the particles was the same. And it is mostly between liquid and solid, close enough that we can call that an equality. Next thing that I want to mention here is called density. I'm sure we've heard the term density. So if something is very dense, it's very packed, very compact. And so it's how tightly the particles of a substance are, how tightly packed they are. And it's also known as mass per unit volume. And so in short, we get the equation D equals m over v. Density equals mass over volume. And so if we would look at that equation, we plug in units for mass and units for volume. Fundamental unit of mass is kilograms, but more often we use grams in a lab. The fundamental unit well, it's not the fundamental, the derived unit that we just learned for volume is either meters cubed, centimeters cubed, milliliters, or liters. And so there we see an array of possible units there of grams per centimeter cubed, grams per milliliter, grams per liter. Could even be kilograms per meter cubed. So we've got a lot of possibilities there. And again, this kind of just goes along with what density means. It's how tightly packed they are. Very simply put, high density is very tightly packed. Low density, there's more spacing involved there. So other measurable quantities of matter, one that we can measure of just about any substance is temperature. Now, sometimes we take for granted what temperature is. There's a key difference between temperature and heat, and that's what I want to identify in these next two slides. Temperature is an average. We take all the particles that are in the sample, and within all those particles, we take the amount of kinetic energy they all bring, and then they average those up, and that's how the temperature is determined. If we increase the temperature, that means that the kinetic energy of the particles has increased, at least on average. Our units here are degrees Celsius or degrees Kelvin. Most of you, I'm sure, have heard of Fahrenheit and Celsius. Most of you probably haven't heard of Kelvin. If you have, that's great. But here is our conversion rate, and it shows you how to convert Fahrenheit to Celsius, Celsius to Fahrenheit, Celsius to Kelvin, and Kelvin to Celsius. And really it's the bottom two that you need to remember, probably just the third one. You will need to know that equation eventually, but right now we're not going to deal with it too heavily. Um, but this next picture here is important. You can see that thermometers in each one, and they're both at the same temperature. However, you notice that the one on the right has much less liquid than the one on the left, and in this case, that's going to provide a different heat content. So even if they're at the same temperature, the substances do not necessarily have the same amount of heat. So what exactly is heat then? Well, if we look at this example, you have two buckets of water, and you apply the same amount of heat to them. They're both at the same temperature. The little cup is going to increase in its temperature much more than the bigger bucket. Well, why is that? The same amount of heat is applied to a very different amount of particles. If we look at the top one, that 50,000 joules is spread out over lots of particles, and the bottom one, that 50,000, is spread out over not nearly as many particles. And so when we look at it in that aspect, it would make sense for that smaller one to heat up more. That's what the idea of heat and temperature are. They're not the same thing at all. Heat is the total amount of the kinetic energy of all the particles. And so if we want to measure heat, we want to understand that it is adding up the kinetic energy of all the particles. So even a substance that has a lower temperature could have the same amount of heat, and that's our example above. Both of those, the bucket of water after the heat was added and the cup of the water after heat was added, actually had the same amount of energy. But the average of the particles that were in it is a much different value. So we see a different temperature, but the total amount of heat is the same, mainly because the bigger bucket has more particles, so it adds up to the same amount. So heat is a sum total. We said before that temperature is the average, heat is the total amount of kinetic energy of all the particles. So if we increase the temperature and the particles, that's what results in an increase in the heat. Another thing we want to mention about heat is how it moves. If you would set an ice cube on a desk, that ice cube does have heat in it. It's a very, very low amount. The particles are barely moving at all, and so its heat content is very, very, very low. The heat around it, though, would be much higher. The heat around it moves spontaneously from the higher area temperatures to that lower area temperature of the ice cube. That's what melts it. Heat moves essentially from hot to cold. That's the nature of heat, and it's spontaneous. It's not in any specific order. It just naturally does it. It doesn't need to be provoked to do that. And so that's an important thing for you to remember, that heat moves from hot to cold. Our units of heat are either joules or calories, and here we see that's just a conversion rate between them, or a conversion factor, that 1 calorie is 4.184 joules. But we really haven't defined either a calorie or a joule, and the calorie was the first that was defined. The joule is just another measurement scale to use. Kind of like the feet was defined, and then if meters were defined later. I think it's actually the other way around, but same idea. A calorie, and this is a very specific definition. It's not the most important one, but I want you to see what a calorie depends on, or what heat depends on. The calorie is how much heat it takes. So calorie is, again, the amount of heat, but it's how much heat it takes to take 1 gram of water and move it from 14.5 degrees Celsius to 15.5 degrees Celsius. I don't want to get into the details of why that's so exact, but by definition, that's exactly what a calorie is. And of course, we see lots of interesting connections with calories. 5 pounds of spaghetti, the calories that are in that could brew a pot of hot coffee. In 1 piece of cherry cheesecake, which is a lot less than 5 pounds of spaghetti, it would actually light a 60-watt light bulb for looks like 1.5 hours. So it's pretty impressive. 217 Big Macs. That's quite a bit of Big Macs, but that would actually be enough energy to drive a car 88 miles. It's pretty impressive. The reason that I even give you the definition of calorie is mostly so we can understand the last measurable quantity of matter, something I'm quite confident you probably have not heard of. It's called specific heat. Now, we said before heat was the total amount of kinetic energy of all the particles. Specific heat, again, is that idea that it's specific. It has certain conditions. So it is the amount of heat energy, but it's how much energy it takes to raise the temperature of 1 gram of anything by 1 degree Celsius. Now, if we go back for a moment here to um, our definition of the calorie, we see the calorie is how much heat is required to raise the temperature of 1 gram of water from exactly 14.5 to 15.5. This is less specific than that. It's 1 gram of anything, of any substance, by 1 degree Celsius. So it is not dependent on the temperature scale, just that it goes up 1 degree Celsius, and this doesn't depend on what the substance is, whereas the calorie was focused just on water. This is kind of a mess, so we have a new math equation. We have Q equals M times C sub P times delta T. And that's one way you can look at it. Q is what stands for heat, M is mass, C sub P is specific heat, and delta T is that triangle, means delta, means change, change in temperature. We'll go over this more in class, of course. But the way we'll actually see the equation is the way I've got it listed here, where Cp, and that's what specific heat is, equals Q, which is the total amount of heat, divided by M and delta T multiplied. M is the mass, and delta T is the change in temperature. And so we'll take a look at that again next class, but please be familiar with what all goes into specific heat. That involves three things: heat, mass, and temperature change. And so here we see a comparison of two different materials. We have a kilogram of gold and a kilogram of aluminum. Hopefully the first thing you notice is the volume that they take up. Same amount of mass, less volume. That makes the gold much more dense than the aluminum. And then again we see something very, very different. It shows that gold heats up about 7 times faster than aluminum. And so as you put the same amount of heat under each of them, gold will go from 20 to 90, whereas aluminum looks like it goes from 20 to about 30 or so. So it shows, and that's what we mean by specific heat. Gold has a higher amount of specific heat based on its properties there. The other idea is that different materials will store different amounts of energy. If we look at this again, 1 kilogram of gold, 1 kilogram of water, we see the densities are much different because of the space that that 1 kilogram would take up. And it also mentions here that water takes about 30 times longer to heat than gold because it stores 30 times more calories. See, gold is a metal, and hopefully you know that metals conduct, meaning they allow heat and energy to flow through them. And so a lot of the energy that goes into the gold will flow right out, whereas the water will tend to store it up, and it'll take much more time to heat it up, even more so than the aluminum before. Here are just a few numbers, specific heats of selected materials. We see aluminum has not even 900, concrete's much lower than that, diamond's even lower than that, glass is a little lower than that, but then you start looking at helium and water, and we see that the specific heat increases drastically. Just various values there. So that's all I wanted to cover with this section. Make sure you know these 5 measurable quantities of matter, and be ready for a section quiz.